Hello, hello, hello. This is Coach Ikram, and welcome to our gas law unit. In this video, we're going to discuss kinetic molecular theory, Avogadro's law, and the differences between real and ideal gases. So we're going to kick things off by talking about what an ideal gas is. So there's two types of gases, real and ideal. And in chemistry, we're going to consider all gases to be ideal. And what does that mean? An ideal gas is any gas that's going to meet 5 basic assumptions of what we call the kinetic molecular theory. And kinetic molecular theory states how particles of any gas are going to move, behave, and interact. So the 5 basic assumptions of the kinetic molecular theory for ideal gases. The first one, gas particles do not attract or repel each other. Second, gas particles are much smaller than the distances between them. Almost all of the volume is going to be empty space. So if you see in this graphic here, we've got a lot of empty space and very, very small gas particles. This is something we talked about in the matter unit. It's what differentiates gases from, say, liquids and solids. This also explains why gases are extremely easy to compress. The third assumption, gas particles are in constant random motion. They never stop moving. And number 4, they're going to move in straight lines until they collide with something. And they could either collide with other gas particles, or they could collide with the sides of the container. That's going to explain why gases will fill any container that they're in, because they'll keep moving until they hit something. No kinetic energy is lost when the gas particles collide with each other or the walls of the container. They maintain their kinetic energy. And number 5, all gases are going to have the same average kinetic energy at any given temperature. So kinetic energy and temperature. Temperature is essentially how we measure kinetic energy. If you have a given temperature, all gases will have the same kinetic energy for that specific temperature. So now we're going to talk about real gases. Most real gases behave ideally. If you've got a situation where you have high temperatures and low pressure, so high temp, low pressure, that's going to support ideal gas behavior. If you've got low temperatures and high pressure, that's going to support real gas behavior. Gases, in reality, are subject to attractive and repulsive forces, and they do exchange energy. But in our course, when we're studying chemistry, we're going to treat real gases like they're ideal, and we're going to follow the kinetic molecular theory. And also in reality, for real gases, smaller gas particles will move faster than larger gas particles at that same temperature, which is something in kinetic molecular theory. We state that all particles are going to have the same kinetic energy at any given temperature. So when gases are heated, kinetic energy increases. Remember that connection between kinetic energy and temperature. So when a gas has more kinetic energy, its particles collide more with the surroundings. So, for example, we've got this balloon. In this first little diagram, it's got a cute little snowflake underneath it. That means that it's got cold. The temperature is lower, which means there's less kinetic energy. So the particles are not moving as fast. Therefore, they are not expanding the walls of that container. This middle balloon is at sort of a room temperature, so to speak. And so those gas particles are moving at a slightly faster speed than they were when it was cold, but still not crazy high speeds. And then here, we've heated it up, so now those gas particles are moving faster, they're colliding more with the container, there's more kinetic energy, and therefore the balloon expands. If the container can expand, the volume will increase. So for example, a rubber balloon. Another good example of this is if you leave a bag of chips in your car over the summer. You'll notice you'll go back to it if you left it in the car for a long time and the bag of chips is large. Because the gas inside the bag of chips has expanded the container. If your container cannot expand, it is a rigid container, like a glass jar, the pressure will increase because that volume cannot increase to withstand the particles moving quicker. So now we're going to talk about Avogadro's law. This is sort of the ultimate common sense law of gases. And what it states is that two different gases of equal volume at the same pressure and temperature have equal number of particles and therefore moles regardless of the identity of either gas. Okay, and under the same sets of physical conditions, all gases are going to behave this way. So if you look at this little diagram here, we've got our first cylinder, we've got 1 mole in here and 22.4 liters. We're increasing the moles of gas by putting more moles of gas and more particles into our container. Therefore, the volume of my container is going to increase. Okay, and that's going to be established by this formula over here. Volume 1 over this N is the number of moles of particles, and then volume 2 over the number of moles. So if you add more gas, the volume of your gas is going to increase. So for example, if you take a deep breath, you're adding more gas, more air to your lungs, and your volume of your lungs increases, hence the reason your chest expands and your diaphragm goes down when you take a deep breath. Second, 1 mole of any gas at standard temperature and pressure is going to contain 22.4 liters of gas. So we've got 3 examples here of 3 different gases. We have argon, oxygen, and nitrogen gases. And if you'll notice, they're all at the exact same volume. There's all 22.4 liters of them. And you note that there's also 1 mole of them, which you know is stoichiometry value we've used in the past on the previous slide. 1 mole is equal to 22.4 liters of a gas at STP, which we do have here. We've got our pressure at 1 atmosphere and our temperature at 273 Kelvin for all 3 gases, and therefore they're all at the same volume, even though they're different gases. So note that the thing that's different here is the mass. Argon is the heaviest, so to speak, with 40 grams, oxygen has 32 grams, and nitrogen has 28 grams. And that is it for this video. In the next video, we're going to pick up on Dalton's law, so make sure that you've taken good notes. Go back and rewatch if you don't understand anything, and come in with questions. And we'll see you in the next video. Bye.